So we have 11.4 here, which is the bell curve, which is something I actually really enjoy quite a bit. The average playing time of CDs in a large collection is 35 minutes, and the standard deviation is 5 minutes. What value is one standard deviation above the mean and one standard deviation below the mean? So what they're asking you to do here, and I'll use some notation you may or may not like, but they're asking you to find the mean, which is a really bad looking mu plus or minus standard deviation. Boy, that looks a lot like a sigma or a theta. So the mean is 35, and one standard deviation above would be plus 5, which is 40 minutes. The other one is the mean minus the standard deviation, which would be 35 minus 5, which is 30 minutes. What values are two standard deviations from the mean? So we're talking about the mean plus or minus 2 standard deviations. So if you take your 35 and you add 2 5s, you'll get 45. If you take your mean and you take away 2 5s, then I guess you'll get 25. So there you go. Part B, assuming the distribution of time is approximately normal, notice that word, approximately normal, about what percentage of times are between 25 and 45 minutes? Less than 20 minutes or greater than 50 minutes? Less than 20 minutes, so and so forth. Draw the curve. Your mean's going to be right back, it's right smack dab in the middle, and it was 35. If you add 5, you'll be at 40. If you add another 5, you'll be at 45. And if you add 5, you'll be at 50. The bell curve goes out 3 directions either way. And then we kind of think about what these regions of space actually hold. You've got your empirical rule that you can look at, but it says these two right here contain 68% of the data. They're each going to be 34%. The next two slices are each 13.5%. Mine may not look it, mine's not drawn to scale. Then we have the 2.35, if memory serves me right. That seems right. 2.35, 99.7. 4.7, yeah, 2.35. Took me a minute there. A little slow today. And then the tail at the end is 0.15. Let's save this so I can erase it a little bit. Anyways, let's do the first question. Percentage of times between 25 and 45. What I would do is I would highlight all of this stuff and I would add it all together. That's between 25 and 45. And it's going to be, you can actually just look at your little sheet of paper. That's 95%. But if you take your little decimals, you take your 34s, you add them together. You take your 13.5s and you add them together, you get 95% of the bell curve. Less than 20. Oh, let's reset the page. Next up is less than 20. That's going to be this little bit over here. It's going to be 0.15%. Greater than 50, and they are the same. Oh, we have the word or greater than 50. Well, that's also 0.15. And if we put this together by adding, we get 0.3%. So less than 20 or greater than 50 is 0.3%. 0.30 if you want to write it. And then finally we have just the straight up less than 20. We already did that math. It was 0.15%. All right, cool. Moving forward. I highlighted part B on this one. I'm going to let you guys do A and C. Suppose your statistic professor returned your first midterm exam with only a z-score written on it. She also told you the histogram of the scores was normal. How would you interpret each of the following scores? And I only highlighted this one. You know what that means is you are 4/10 of a z-score below average. So the reality is you're not too much below average. You're just a little below average. Now I'm going to say something. If you can't figure this out, if you can't figure out C, you are below average. I probably shouldn't talk like that, but if you can't figure out part C, you're below average, kids. You need to focus on your studies. Anyways, I'm leaving that for you. Apparently I'm doing number 5. The red blood cell count for a population of adult males can be approximated by a normal distribution with a mean of 5.4 million per microliter and a standard deviation of 4 million cells per microliter. What is the minimum red blood cell count that can be in the top 16% of counts? What is the maximum that can be in the bottom 2.5% of counts? So again, I draw I understand you could just look at a picture, but the goal is retention here. We have a middle of 5.4, and we always go 3 above and 3 below because that accounts for 99.7% of the graph. The little tick mark's probably too close. But if I take away 4/10, I'm at 5. If I take away 4/10 again, I'm at 4.6. If I take away another, I'm at 4.2. If I start at 5.4 and I add 0.4, I'm going to be at 5.8, then 6.2, and 6.6 because I'm taking 5.4 and I'm adding 0.4. And I'm going to go ahead and I'm going to sign my percentages. Again, this is not drawn to scale. Please understand that. These are 34%. These are 13.5%. These are 2.35, 2.35. And this little guy right here is 0.15, as is this little guy right here, 0.15. Now I want the red blood cell counts that could be in the top 16%. It turns out if you take these 3 numbers and you put them together, you get 16%. So top 16%. And again, I know this is something that gets kids. 13.5 plus 2.35 plus 0.15 is 16. So I'm looking at all of this. What is that? That is going to be blood cell counts above 5.8 million cells per microliter. So when I talk about my top 16%, I'm talking about values, we'll just use X, being bigger than 5.8. All right, bottom 2.5%. That's going to be these 2 guys right here. Because if you take 2.35 and you add 0.15 together, you get 2.5. So for that one, your bottom 2.5%. I have to have values coming in that are less than 4.6. And again, I'm just letting the descriptor variable be X. There you go. Drawing a curve. That's all there is to this stuff. All right, a large population has a mean of 310 and a standard deviation of 37. We have no idea what it's about. Who cares? Draw out a normal curve, label the values at 1, 2, and 3 standard deviations away from the mean. Then using the empirical rule, which is what we're doing, find what percentages of the observations fall in the intervals the mean plus or minus a standard deviation, the mean plus or minus 2 standard deviations, and the mean plus or minus 3. And again, I'm only doing the one in the middle. You guys do these. I'm not doing those two. Those are for you. The mean is 310. If I add 37, I'd be at 347, I think. The next one ought to be 384. And then I'm going to add 37 again. Just hit a wall there. It'd be 414, 421. That seems right. You should probably check me. I should probably check me. Let's check me. 384 plus what? 37? Yeah, 421. If I take away 37, seems like that's going to be 273, not 273, 263. Sorry, kids, I just had like a moment of stupidity hit me. It happens. 273. I said it right the first time. Even I get tired. In fact, I'm just going to keep doing this again just to show you that sometimes even I have bad days. There we go, 236. And then that one I can do in my head, 199. And then I just draw stuff out. Again, it's 34 in each one of these two block boxes. Can't even talk. 13.5 in each of those. 2.35, 2.35, and 0.15 of a percent for the tails. So anyways, the mean plus or minus 2 theta is going to be the middle ground. Sorry, I'm only doing this one. The mean plus or minus 2 theta is going to go back here and over there. It's going to be all of this. And, you know, that's going to be 95% of the graph. It doesn't look like it because my bell curve is not the scale, but that is 95% of the graph. Scales for an IQ test are approximately normal with a mean of 100 and a standard deviation of 15. The organization Mensa, which calls itself the High IQ Society, requires a score of 130 or higher. What percentage of adults would qualify for membership? Oh, look, draw the curve. If you don't know how to draw this curve yet, you are obviously not going to get an application to Mensa. They look down on people like you. Oh, I'm just not being very nice today, am I? This is the guy who just had to use a calculator to do basic math. Anyways, and also the standard deviation is not 30, it's 15. Seems like in the state of Tennessee, we call you gifted if you have an IQ of 125. $70 minus 15 is 55. 145. Then we throw the stuff on there and we go to town with it. And again, I'm just doing this for memory. This is what, the 4th time I've done it already? Who knows? I don't even keep count. And I'm literally not thinking. You see these numbers appearing up? There's not a thought in my head going on. It's all my hand that's doing it. Every bit of it. You draw it so you know the numbers. If a kid asked me in 10 years after I quit teaching math what the empirical rule was, I would draw this curve. I wouldn't even think about it. I'd draw the curve and be like, there you go. That's what the empirical rule is. Anyways, to be in Mensa, you have to have 130 or higher. It's not much of the population, is it? It's just a small 2.35 plus 0.15. So only about 2.5% of all people have an IQ of 130 or higher. I haven't taught all that many students, maybe 7 or 8 that actually we knew what their IQ was. So far this year in a statistics course, you have received the following test scores: 75, 82, 54, 87, 76, 67, and a 68. Find the mean and standard deviation for your test scores. We're going to do that in a calculator. So that was go to Stat, go to Edit. I'm going to clear out what's in my list. (82, 54, 87). 76, 67. 68. For those of you who are just blindly copying, you need to make sure you know how to use a calculator. 75, 82, 54, 87, 76, 67, 68. Anyways, I'm going to quit out. Second quit. You don't actually have to quit. Stat, Calc, one variable statistics. So the average is going to be 72.714. Standard deviation, sigma of x, is 10.081. Now, if you score a 92 on your next test, what would its corresponding z-score be? A z-score is going to be your result, take away the mean, divided by the standard deviation. So if you score a 92, your result would be 92. You're going to take away the standard deviation of 72.714. You're going to divide it by that 10.081. I don't feel like hitting math, num n over d, so I'm just going to do this in 2 steps. I don't know whether it's better to teach things doing all at once or to just show kids just to do multiple steps. I just don't know anymore. Anyways, it's about 1.913, which is way above average. It really is. If you score a 54, what would its corresponding z-score be? Well, this one will be negative because this is below your average. Your average was 72. This is definitely below average. I'm going to have a negative result. So I'm going to take that 54, I'm going to subtract the mean, and I'm going to divide by 10.081. Now, the truth is, your scores are not normally distributed, but whatever. We're trying to find a z-score. Yeah, you were way below your average, negative 1.856. Alright, if you wish your next test score to be at least 2 standard deviations above your previous mean, what do you need to make? So your previous mean was 72.714, and you're going to add 2 of those 10s. You're going to see what that is. So 92.876. So you have to make above a 92.876. Because I had the wording at least. Anything above that's going to do the job. So 93 or higher is what you're after. Alright, I think these are technology problems. Like number 12 is a technology problem. These are technology problems because these probabilities do not exist on the bell curve. They do, but they don't. Okay? They're not anything that we've defined as easily and able to do. So heights in Dresden High School for males are normally distributed with a mean of 68 inches and a standard deviation of 1.5 inches. And yes, I made those numbers up. Find the following. The percentage of DHS makes, I should say males, whose heights are between 5 foot and 5 foot 8. Now 5 foot is going to be 5 times 12, 60 inches. And 5 foot 8 is going to be 60 plus 8 inches, 68 inches. And again, we kind of get to cheat on this, so we're going to use a function on your calculator called, I had a brain fart here, I'm pretty sure this is the normal CDF. Second, VARS, yeah, the normal cumulative density function. So we're using normal cumulative density function. Because if I was to write out what I have here, if I took away a whole bunch of 1.5s, I wouldn't get to 60. It's just not going to happen. And if I added some 1.5s, I wouldn't get to 68. Now this is going to be the vast majority of males. It is. Well, sorry, we have a mean of 68. This is going to be half the student body, more or less. The lower boundary here is going to be 60 inches. The upper boundary is going to be 68. And the mean here was 68 inches. Look at that, just a little over 50%. It's kind of weird that they have it at 5 at the end. But anyways, it's basically 50%. It's equal to 0.500000005 or 50%, as it should have been. Because 60 inches is less than 4 standard deviations from the middle. The probability of being less than 6 foot tall. So if you're 6 foot tall, you're 72 inches tall. Now when we think about how normal CDF works, this is going to be what we call the upper boundary. So second, VARS, normal cumulative density function. The lower boundary, a lot of times we just make up numbers, but we'll do things like 1 times 10 to the negative 99th power. Sorry, we should do something like -1. The newer calculators actually usually have that as a suggestion. But the reality is you can use something like 0. 0 inches height doesn't make any sense. The upper boundary is 72 inches, and the mean was 68. Oh, and I need to go back to the question I just did because I forgot to get sigma. Sigma is 1.5. So let me retrace. After I do this one, I'll do number 1 again. Anyways, that doesn't make a lick of sense, does it? Because I did it wrong. Being less than 6 foot tall is the upper boundary. That seems wrong. No, it doesn't. Most people are going to be less than 6 foot tall. I'm getting tired. I had something in my head. Let's say 99.6%. That should be more or less true. Now, I screwed up on number 1 because I forgot to put the standard deviation in there. On number 1, we had what is the probability, the percentage of DHS males who are less than 68%. The lower boundary is going to be 0. The upper boundary is 68. The mean is 68. And the standard deviation is 1.5. I didn't do that the first time around. It actually turned out to be the same thing. So, cool. No loss. The exact probability of being a 5'9" tall male. This is actually the normal PDF function. It does the exact chance of one outcome. So the exact probability of being a 5'9" tall male. So second, VAR's normal PDF. If you're going to be 5'9", you're going to be 69 inches tall. The mean is 68, and the standard deviation is 1.5. Surprisingly high, 21.3%. Wouldn't have guessed that. 21.3%. What percentage of males are less than 5'7"? Again, 5'7" is 5/12 plus 7, which is 67 inches. And if we're talking about less than, this is going to be an upper boundary. And we'll set our lower boundary be 0. That's going to be a normal cumulative density function. Second VAR is normal cumulative density. Lower boundary of 0. That one actually had the suggestion. Upper boundary of 67. Mean of 68. Standard deviation of 1.5. I expect this to be a good chunk, 40% plus. Oh, I was wrong. 25.25%. I thought it'd be higher than that. But it was not. What percentage of males are greater than 5'11"? We're going to do the same thing. We're going to do normal CDF, but 5'11", which again is going to be 71 inches, is going to be your lower boundary here. Now, if you're wondering why I'm doing that, because I'm kind of thinking like 71's over here, I'm talking about people above. Still thinking about the bell curve, by the way. So second, VAR's normal cumulative density function. The lower boundary is going to be 71. I'm going to make up a ridiculously height of 120 inches. It can be anything. It's not going to matter too much, but it needs to be a ridiculous number. There's not going to be many males above that height. According to that, about 2.3%. What was the probability of being 6 foot tall? I never did 3, did I? More than 6 foot tall. Second, VAR's. Oops, let me quit out of this. Second, VAR's. Normal CDF. More than 6 foot tall is going to have a lower boundary of 72. Same upper. Apparently I don't need to be recording. Even smaller yet, 0.38%. Alright, there's 13. That'll help you do 12. Then we have the EOC stuff. The prices of items at 2 different supermarkets are shown. Toilet paper at store A cost $4.99. You can kind of see it right there. And at store B it's $6.99. So what I just learned is the top row is toilet paper. Because I can read. Toothpaste at store A costs $2.99 and store B costs $3.25. So the bottom row is toothpaste. The first column is store A, the second column is store B. Which statement is true about the matrix? The second column represents the price of toothpaste. That's wrong. The second column is store B. The first row represents the price of toilet paper at both supermarkets. That is the true statement, but let's just go through the rest of them. The second row represents the cost of toothpaste. No, columns are the stores. And the first column represents the items of store B. That's wrong. It's store A. So yes, it was choice B. Usually on questions like this, about 15 to 20% of the student body misses it. No one is supposed to miss a question like this. The coordinates of a triangle's vertices are given in the matrix T. The matrix twice T represents the coordinates of the triangle's vertices after a transformation. What is twice T? Not that you want to be bored by concepts like this, but this is called scalar multiplication. That's all it is. And you quite literally multiply everything inside the matrix by 2. That's what you do. So I'm thinking right now about 2 times 4. It's 8. I'm thinking about 2 times 4 because I saw 4. And 2 times 4 is 8. Oh my God, I just finished the problem. Because nothing else had an 8. Moving on. 2 roads will be built. The given matrices represent the length of each road that is paved and unpaved, and the cost to build each mile of paved and unpaved road. The products of these matrices represent the total cost of each road in thousands of dollars. What is the product of these 2 matrices? This is likely a by hand question. I don't think it'll be on the calculator part. What we do is we multiply rows and columns together. It's actually called a dot product in some sense, but we multiply rows by columns and we add down. That's how it's done. Plain and simple. I don't care if you don't understand why we do it that way. That is how we do it. So here's the first row, and I'm going to turn her sideways. She's 4.5 and 0.4. And here's the second. That was the first row. Here's the first column. 580 and 65. Now, it's going to be a pretty good sized number. So I got to figure out what 4.5 and 580 makes. Well, 4 580s, and this is kind of how I do things, 4 580s is going to be 2,320. And half of 580, which is something most people should be able to do, is going to be what? 290. I just add down 11, 4, 6. Well, evidently I made a mistake there somewhere. Oh, because I'm not done. 2610. Now I'm going to take 4/10 of 65. Here's how I do that kind of stuff in my head. 1/10 of 65 is 6.5. And then I turn around and I multiply it by 4. And sometimes I break that up too. But that's 24 plus 2, which is 26. And then I add down. 2636 is what I better be seeing. It's choice A. Because that one had 2636. Anyways, old school math, kids. It always wins. Hey, and I'm done. Sweet. It's school because the lunch bell rang.